Hello. Today we are going to cover the first section in Calculus 2. It's section 6.1, Area Between Curves, Application of Integration. When you finished Calc 1, you had learned how to find the area under a curve. So today we're going to explore how to expand that, the area between two curves. So this is what we had learned in Calculus 1. We said I want to integrate from a to b the function f of x dx, which is equal to the limit as n approaches infinity of the summation I equals 1 through n of x sub I asterisk delta x. And so here we have a function, some general function called f of x. We have the points a and b, and we want to find the areas. And what you learned to do is you created these rectangles, right? And you had the same size rectangles over and over again. And you found that when you found the area, you made this rectangle smaller and smaller, blah, 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 all that other wonderful stuff. And then we summed them up. Well, we're going to expand that. So instead of finding the area between one curve, we want to drop some strips here. But if we pay attention, what we should see is that the area between the two curves is not exactly what we want. I mean, what we have here is the area between here and here. We don't care about this white space here, what I highlighted in green. What we care about is what's in yellow. So what we would do then is we could say we would find the area between the two curves. We would take the area of the larger curve, or the higher grade function y equals f of x, and subtract the area of y equals g of x. So here's the first problem. We have the function find the area of the region bounded above by y equals x squared plus 1, and bounded below by y equals x, and bounded on the sides by x equals 0 and 1. So given the function, and we're just going to sketch this, we should know that y equals x squared is a parabola like this. So we're going to call this y is equal to x squared plus 1. And then we need the function y equals x, which is just a line through the origin, such as this. We want the area bounded between the two from 0 to x equals 1. So we're just going to call this line here x equals 1, and this line x equals 0. So we want that area, but we only want the area, like I said, between the two. So we want just this area in yellow. We don't want the white space. So here's what we're going to do. We're going to take the function, we're going to integrate. This is how we've done it in Calculus 1. We integrate from 0 to 1. And we're going to take the top function, which is x squared plus 1. And we want to subtract from it the area of the other function, minus x, because we don't want that information. 0 to 1, dropping the parentheses, x squared plus 1 minus x dx. And from here, it's just simple integration. We get x cubed over 3 plus x minus x squared over 2. And we're going to integrate that, or evaluate from 0 to 1. In case we don't remember what to do, we're going to put the 1 in first, so it's 1 over 3 cubed plus 1 minus 1 squared, which is 1 over 2. Subtract from it the results of everything over here is going to be 0. And then the final answer is 5/6. So the total area of the part in yellow is 5/6. So now let's move on to this next problem. It says find the area of the region enclosed by the parabolas y equals x squared. Well, that's easy. That looks like this. Y equals x squared. And then we have another function. And that's 2x minus x squared. And that looks something like this. So in here, we want to find the area only contained in between these two. And I'm going to just draw a little strip here to remind myself what I'm doing. And I can see that there's white space. And again, this is y is equal to x squared, and this function is y is equal to 2x minus x squared. These are functions that you should be able to figure out how to draw without a calculator, by the way. So I want to integrate. So how do I find out where to integrate from? Well, I set the two equations equal to each other because that's where the intersection points are. I set them equal to each other. I move everything to the one side. 2x squared minus 2x is equal to 0. Factor out of 2x. I get x minus 1 equals 0. So they intersect at x equals 0 and 1. So I'm going to integrate from 0 to 1 because this point here is 0 and this point here is 1. I don't really care what the y value is. I just need the x because that's what I'm integrating from. Now I need to take the top function, which in this case is the y equals 2x minus x squared because that's what's the top of my strip is touching. 2x minus x squared, and subtract from it the bottom function, which is x squared. And I'm taking the dx of this. So I'm going to drop my parentheses. I get 2x minus 2x squared dx. I'm going to evaluate this. I'm going to, take the integration of that. X squared minus 2/3 x cubed from 0 to 1. And then I'm going to evaluate that. And I get 1 minus 2/3, subtract 0 for everything else. And my total area is 1/3. Again, that's how we're going to find the area between the two curves. So now let's look at the next one. Find the approximate area of the region bounded by the curves y equals x all over the square root of x squared plus 1 and y equals x to the fourth minus x. Use a calculator to do the integration. So this is a problem where I need my calculator. Okay, now as you can see, I have my calculator up, and I'm going to put in, to save some time, I already put the functions in. In y sub 1, I put the function x over the square root of x squared plus 1. As you can see here, it's my y sub 1. And y sub 2, I put the function x to the fourth minus x. I can graph this, and I want to see where the two functions intersect. It looks like the first one's function's intersecting at 0. So I'm going to find out where the second one the second intersection is. So I go to second, calculate. I go to the intersect command 5. I'm on the first curve, which is the blue curve. So here it is. I'm going to go to the left of where I want to intersect. And then the red, I'm going to go actually above. I'm going to scroll until I get past, because I want to make sure it picks this intersection point and not that intersection point. Hit enter. Ask me to guess. And there it is. It's saying it's 1.1800, blah, blah, blah. So what I'm going to do is I can't remember that number, and I want to have as precise of a value as possible, so I'm going to clear this. I'm going to say second quit. Now what's interesting is that's stored already in x. So if I put x here and I hit enter, there's that number, 1.180775. I'm going to store it. So I'm going to hit store, alpha, and I'm going to choose to put in O. Enter. And now O will have the same representation. So now let's look at what the calculator is going to do to calculate that integration. I'm going to hit math. Down here is fn int, which is choice 9. Now this is set up with the newer software. I will quickly write out what you should write when you're using the older software. I want to start my integration from 0. Scroll up. I wanted O. That's what I stored that second intersection. So alpha O. There it is. And I want my first function, y sub 1. So to find that, I hit vars, scroll to y vars, click enter for function, and the first choice is y sub 1. And from there, I want to subtract my second function, vars, y vars, function, but now I want choice 2. And I'm integrating this with respect to x, so I have to tell it x. I'm going to hit enter. And there's my answer. So we're going to drop this down here. Okay, it looks like something's funky is going on with the screen, so we're just going to finish this problem. As you can see here, I have got my answer that I was looking for. We're going to go to 3 decimal places, 0.785. If you have the older software, you're going to use your calculator and you're going to go in and find the fnint command. This is your functions you want to subtract from each other. I'm going to integrate with respect to x, and then my a value, my lower bound, and then my higher bound. So we did from 0 to O. Then hit enter, and then again, you'll still get this answer of 0.785. That's again using the older software. So let's move on to the next slide. It says the area of the region between two curves and x equals a and x equals b. It says if I integrate from a to b, the absolute value of f of x minus g of x dx. If I do that, I should have no problem. I choose not to use this concept. It's given me some problems in the past. I'd just rather break them up. So, looking at the next problem, so here's the next problem. It says find the area of the region bounded by the curves y equals sine of x, which I had already drawn in red, and y equals cosine of x, which I've drawn in black, from x equals 0 to x equals pi over 2. And if we look, we can see that all I care about is the area, and I'm sorry my curves aren't exactly the way you should look, but there's two different regions. Once sine is on top, and once at one point cosine is on top. So when we're looking at a problem like this, we can do the absolute value, which I don't like to do, or we can just break them apart. I tend to break it apart. Again, my drawing is not to scale, but if we pay attention, the problem is really symmetrical. So that being said, I can say, well, I know looking at the function from 0 to pi over 4, and that would be this region here. Again, it's not drawn to scale, but it is symmetrical. Well, I could take that area and double it. And then I could just say my top function is cosine of x, subtract from it sine of x dx. Or, if I don't see that, I could just go from 0 to pi over 4, cosine of x minus the sine of x dx, and add to that from pi over 4 to pi over 2. But then I have to switch them, because sine of x is on top. So now I have to go from sine of x minus the cosine of x dx. Well, I'd rather just integrate once and then just double my value, so I'm going to do what I have on the left-hand side. I get 2. I get sine of x plus cosine of x. And I'm evaluating from 0 to pi over 4. The reason I get positive cosine of x is because the derivative cosine of x is a minus sine of x. I already have a minus sine of x. So I already have that taken care of for the sine. Then I have to evaluate that, so I get 2 times the sine of pi over 4 plus the cosine of pi over 4. And then I need to remember what that is. If I don't remember, I can remember my handy-dandy triangle, pi over 4, square root of 2, square root of 2, 2. So I'm going to have 2 times the square root of 2 over 2 plus square root of 2 over 2. I end up with adding this together, 2 times, I got a mistake here. Oh, you know why? Because I forgot to do the rest of the problem. Not thinking today. So that only took care of the evaluation from pi over 4. Sorry. From that, I have to subtract sine of 0 plus cosine of 0. Sine of 0, well, that's just 0. And cosine of 0 is a positive 1. So if I distribute, I end up with 2 square root of 2 minus 2. And that's the area for that. Just a quick note. In this class, 1 over the square root of 2 is fine to write. You don't have to rationalize and give me square root of 2 over 2. It's okay to leave square roots in the denominator. So the answer for this one, again, I forgot to evaluate the sine of 0 and the cosine of 0. Turns out to be square root of 2 times the square root of 2 subtract 2. We're almost done. We have 2 more problems left to work out. This one is I want to see what this function looks like. Y is equal to the absolute value of x. So y is equal to the absolute value of x. I'm going to fix that in a second. So this is about y is equal to the absolute value of x. And then I have to have the function y is equal to x squared minus 2. And again, these are functions I should be able to figure out what they look like. It looks something like this. It's a y equals x squared, but lowered 2 units. Right? I want to evaluate this. But if I pay attention, some things I should note to myself, y is equal to square root absolute value of x. Well, this line here is y is equal to x line, and this line here is y is equal to the opposite of x. It's important to note that because I can't evaluate where from both points. They're 2 different lines. I should pay attention that they're symmetric, find out where they're equal, so I'm going to say x, the absolute value of x, or x is equal to x squared minus 2. And that x squared minus x minus 2 is equal to 0. I get x minus 2 times x plus 1 equals 0. X is equal to 2 negative 1. Well, obviously negative 1, that would be this line continuing down. I don't want that point. But I can evaluate from 0 to 2. So I'm going to evaluate from 0 to 2. That allows me to just look at this area between these 2 curves. And then I can double it because it's symmetric. So anytime we have something symmetric, I'm going to take advantage of it. That line on the right-hand side is the y equals x line. The other line on the left-hand side of the y-axis is the minus x line. So my top function is x. I want to subtract from it my bottom function, x squared minus 2 dx. I'm going to drop my parentheses. So I get a minus x squared plus x minus 2 plus 2 dx, because the double negative there. Then I'm going to evaluate, I'm going to integrate, so I get a minus x cubed over 3 plus x squared over 2 plus 2x. And I'm evaluating all that from 0 to 2. So I'm going to put 2 in, minus 2 cubed over 3 plus 2 squared over 2 plus 2 times 2. Subtracting, they're all going to be zeros. I'm going to calculate all that. I'm going to double it, and I'm going to get the final answer of 20 over 3. It's 20 over 3. All right. There's one more function I'd like us to look at. You have a problem like this on your homework. It says use calculus to find the area of the triangle with these vertices. So again, I need to come up with a triangle. And this is a sketch. It's not exact, but I have points 0, 5. I have another point 2, negative 2. I'm going to call this 2, negative 2. And I have a point 5, 1. And each one of these is connecting a line of some sort. So let's do that real quick. I'll have a red line from here to here. I will have a blue line from here to here. And we'll pick another color. Let's pick green from here to here. So the trick at this point is, first of all, if I pay attention, I know a couple things. This point here is an X value. So I'm going to find the area between the lines from here to here. And I'm going to find the area between the lines from here to here. So I know where I'm going to integrate. I know as far as integration, there's going to be one where I'm going to integrate from 0 to 2. And then I'm going to add to that the integration from 2 to 5. But I need to know the functions for each one of those. So I'm going to call this A, I'm going to call this B, and I'm going to call this C. I'm going to give you a moment to work out how to find the slopes and then the equation of the lines, and then I will come back and show you what I have. So here we are. I went through and I found it. So from 0 to 2, I have line AB subtract line AC. So first I have to find their slopes. Here I have slope of AB. The slope of this AB. It's 5 minus 1. I end up with a slope of negative 4/5. And I know that the line is y equals minus 4/5 x plus 5. Then I have to find the equation for AC. It has a y-intercept of 5. I find the slope is negative 7/2. Y is equal to negative 7/2 x plus 5. Lastly, I need to find the line, the equation line from CB. So I find the slope, which is equal to 1. And I find out the equation is y equals x minus 4. So here's what I have. I need to integrate from 0 to 2 minus 4/5 x plus 5. Subtract from it the lower function, minus 7/2 x plus 5 dx. And to that, I want to add, from integrating from 2 to 5, negative 4/5 x plus 5, and subtract from that x minus 4 dx. After integration, I'm just going to give you the answer. You should get 27/2. This is something you should be able to do on your own at this point. The hard part was coming up with each one of the functions, understanding what it's asking me to do. This concludes the first lecture. Thank you very much, and I look forward to seeing you all in class.